This 3D illustration shows a simple rectangular beam reacting to force. When we push down on its wide, flat face, it bows heavily. But if the beam rotates 90 degrees, applying the exact same force to the thin edge produces zero deflection. The material hasn't changed, the mass hasn't changed. The only difference is how the area is arranged against the bending force. We measure this geometric resistance to bending using a property called the area moment of inertia. Structural engineers specifically separate the area moment of inertia from the mass moment of inertia. While mass moment tracks physical wake and rotational resistance for moving objects, area moment deals entirely with the two-dimensional distribution of a cross-section's area. We are looking strictly at geometry. This diagram displays a 2D cross-section of a rectangle with a horizontal x-axis drawn exactly through its geometric center, known as the centroid. For any standard shape, the lowest possible moment of inertia always occurs at this exact center point. For a rectangle, the baseline formula for this centroidal axis is width times depth cubed, divided by 12. The most common mistake here is mixing up which dimension gets cubed. The rule is absolute. You always cube the dimension that is strictly perpendicular to your axis of interest. Since our x-axis is horizontal, the vertical depth, or d, is the dimension we cube. Manipulating how area is distributed away from this centroid is how structural engineers design beams that span massive distances without collapsing under their own weight. But we often need to calculate this value when our axis of rotation isn't perfectly in the center. Look at this animation as the axis detaches from the centroid and slides down to sit exactly at the base of the shape. Our baseline formula no longer works here. We need a new tool. We solve this using the parallel axis theorem. This states that the new moment of inertia equals the original centroidal moment plus the total area of the shape multiplied by the shift distance squared. Let's put this into practice. Pause the video right now. Calculate the moment of inertia for the rectangle's base using the parallel axis theorem. The shift distance to the base is d divided by 2. Let's check the math. This diagram shows the step-by-step algebra. We take our centroidal formula, bd cubed over 12, and add the total area, b times d. We multiply that by our shift distance, d over 2 squared. By expanding and finding a common denominator, the math resolves perfectly into a new base formula, bd cubed over 3. Because the formula adds area multiplied by distance squared, moving an axis away from a shape's centroid will always mathematically increase the moment of inertia. You are forcing more of the shape's area further away from the bending point. Real structures rarely use simple rectangles. This animated diagram shows a complex composite shape, an L-beam. To analyze this, we slice it into simple, familiar geometries, labeling them Area 1 and Area 2. Solving a composite section requires two initial steps. First, you calculate the global centroid of the entire L-beam to establish your master axis. Second, you isolate Area 1 to apply the parallel axis theorem. Pay close attention to the shift distance here. The value yc1 is strictly the distance from the local center of Area 1 to the global master axis. It is never measured from the bottom of the shape. You repeat this exact process to find the moment of inertia for Area 2. Then you simply add the two values together. The total moment of inertia for the composite shape is the sum of its parts. Breaking complex problems down into foundational geometric shapes allows engineers to analyze virtually any structural profile using simple addition. This diagram shows the x and y axes laying flat across our section. If we add the moments of inertia from both of these flat axes together, we get the polar moment of inertia. This describes the section's resistance to rotating around a perpendicular z-axis, which is essentially its structural resistance to twisting forces. We can also express bending resistance as a physical distance using the radius of gyration. This animated diagram demonstrates taking the entire area of our shape and squeezing it down into an infinitely thin strip. The distance k is the exact theoretical radius where you can place this strip without losing any of the shape's original moment of inertia. A higher radius of gyration means the area is distributed further from the center, creating a highly efficient structural shape. This geometric principle explains why hollow tubes and I-beams dominate modern construction. Our calculations so far have focused on standard moment of inertia, which is always a positive value, but there is a secondary metric called the product of inertia. Instead of bending resistance, this measures structural asymmetry, and its value can be positive, negative, or exactly zero. This diagram overlays a symmetrical I-beam onto a standard Cartesian plane. Because the geometry is symmetric, the positive XY products in the top right quadrant perfectly mirror and cancel out the negative products in the bottom right. The algebraic sum of these areas resolves to zero. When the product of inertia is zero, engineers know they have found the principal axes, where a beam will bend perfectly straight without any dangerous twisting. Let's consolidate everything into a master reference guide. You will want to take a screenshot of this upcoming summary, as it contains every mathematical tool required to solve standard structural problems. This split-screen graphic presents our foundation on the left. These are your standard baseline formulas for the centroidal moment of inertia across rectangles, triangles, circles, and semicircles. On the right, we have the 4-step checklist for solving composite sections. Break the shape into parts, find a global centroid, apply the parallel axes theorem, and sum the results. Below that are your equations for polar moment and radius of gyration. And remember the cardinal rule: always cube the dimensions strictly perpendicular to your axes. These rules turn structural analysis into a repeatable geometric process. Instead of recalculating the integration for every cross-section from scratch, you can now build and analyze professional structural profiles using simple, reliable math.